Welcome students in this session AC through pure resistor, inductor and capacitor. Now for the exam purpose we have to understand only reactance, but the value of a reactance came when we understand the each phenomena in a brief. So let's begin the topic. The first topic is a phasor or phase of AC. The term omega t is a phase of alternating current EMF, and it is defined the fraction of a time period that has elapsed since the current last passed its zero value in a positive direction, as you can see over there. So phasor diagram, if I'm just talking about what is it, so the quantity that has a magnitude and direction in the time domain, that is vector that changes with respect to time. A phasor diagram represent alternating current and EMF. We know that alternating current and EMF both are very sinusoidally with respect to time and the same frequency. They will not be in the phase. Depending on the circuit, current may lag or lead the EMF. The study of such kind of a circuit becomes easy if alternating current and EMF are represented by vector in a plane. The graphical representation of alternating current and EMF as vector is called as phasor or Argand diagram. This is the diagram of phasor diagram of alternating current. As you can see over there, like this. So here E naught is what? It is the peak value. It is the peak value. The component is changing with respect to theta. So theta we can represent as an omega t. Angular displacement is equals to angular speed into time. And if I'm just taking omega in terms of a trigonometric function, that will be treated as angular frequency. Okay, so here E is equals to E naught sine omega t, where omega is equals to 2 pi by t. Okay, this is taken as an angular speed. So angular speed theta by t, theta will be 2 pi complete circuit and divided by time interval. So this is the value of actually omega, which here this will be angular speed. AC through pure resistor. If the alternating current have only a resistor, this is called as a AC have a pure resistor. The alternating EMF, which we know that E is equals to E naught sine omega t. So for that scenario, consider a resistor of a resistance R, let an alternating EMF of a instantaneous value E is equals to E naught sine omega t be applied to the resistor. The voltage across the output of the AC source varies with time according to E is equals to E naught sine omega t, or V is equals to V max sine omega t. What E showing will be there? This will be E showing EMF. And what V showing here? This is a potential. So if I'm supposing this is the first equation, then where E and V are the instantaneous potential differences. So according to the Ohm's law, I is equals to V by R. So I is equals to V max sine omega t by R. Or we can say that I is equals to V max by R. What we can say that this is the I max by R. Understood? And sine omega t will be there. This is the equation number 2, where I max is equals to V max by R. Now from equation 1 and 2, it is clear that voltage and current are in the same phase. So the phase difference between the voltage and current will be 0. It is represented by phasor diagram, as you can see over there. So they are in the same phase, as you can see here. They are in the same phase. That's why it is called as a phasor diagram for a resistance only. Similarly, what we have AC through pure inductor. As you can see in this diagram, in the circuit there will be no resistor or any other term. There will be only inductor. A single inductor will be inserted over there. We know that the value of a EMF, that is the minus LdI by dt, will be Q. And E is equals to E naught sine omega t, or we can say V is equals to V naught sine omega t. So an alternating voltage applied to an inductor of inductance L as shown in the figure, such that a circuit is known as purely inductive circuit. The alternating EMF or voltage applied is given by E is equals to E naught sine omega t, or V is equals to V naught sine omega t. This is the first equation. The induced EMF across the inductor is minus LdI by dt, which opposes the growth of a current in the circuit. So as there is no potential drop across the circuit, so E plus minus LdI by dt is equals to 0. LdI by dt is equals to E, or we can say that di by dt is equals to E by L. So di by dt is equals to E naught by L sine omega t, or we can say E is equals to E naught sine omega t. So di is equals to E naught by L sine omega t dt. If we do integration both sides, so dl, we have to take an integration of E naught by L sine omega t dt came in the nature. Now integration of a sine omega t will becomes minus cos omega t by omega. So here what we get, E naught by L omega minus cos omega t, as we solved here. So the final result will become I is equals to I naught sine omega t minus pi by 2 from equation second. Because minus cos omega t we can write as a sine omega t minus pi by 2. Now where I naught is equals to E naught by L omega, it is called peak current. So from equation 1 and 2 we can find the phase of EMF is omega t and the phase of the current is omega t minus pi by 2. Hence the phase difference between the EMF and the current is a pi by 2 radian or 90 degree. The phase difference between the EMF and current is a pi by 2. Therefore, the current lag behind the EMF leads the current by pi by 2 radian or a 90 degree. It is represented by the following phasor diagram. As you can see over there, the value of a current is a negative from the equation like which we got previously. So here, because of the negative value of a pi by 2, the value start from there. Inductive reactance. So inductive reactance is defined as the opposition offered by an inductor when current flows in it. It is given by XL is equals to omega L is equals to 2 pi FL. From equation second, we know that like I naught, which is the peak value of a inductor. So I naught is equals to E naught divided by L omega. Comparing with the I naught is equals to E naught by R. So the term L omega is known as work as a actually resistance, or we are saying as an inductive reactance, denoted as a XL. So I naught sine omega t minus pi by 2, this is the value of I, and where omega is equals to 2 pi F, F is the frequency of AC. The unit and dimension of inductive reactance are same as that of resistance R, like ohm. In terms of XL, the RMS EMF is ERMS is equals to IRMS into, like we are taking earlier what we are taking, V is equals to IR. Similarly, ERMS is equals to IRMS. In the case of inductor, we are just putting the value XL over there, where IRMS is the root mean square value of a current through an inductor. Unit of XL or R is ohm. Dimensional formula ml to T minus 3 A minus 2. AC through pure capacitor. If I'm just taking a pure, like a one single capacitor, there will be no other devices will be inserted on that. So we are just taking capacitor as a C. An alternating EMF or a voltage applied to a capacitor of capacitance C as shown in the figure. Such a circuit is known as purely capacitive circuit. The alternating EMF applied across the capacitor is given by E is equals to E naught sine omega t, or V is equals to V naught sine omega t. This is the first equation. Let Q be the charge on the capacitor at any time. Potential difference across the capacitor is V is equals to Q by C is equals to V naught sine omega t. And if I just calculate the value of a Q, so this will becomes V naught C sine omega t. Differentiating with respect to time, the result will get dq by dt is equals to V naught C omega cos omega t. Now the term which we can write over there dq by dt as an I, V naught C omega cos omega t. So I is equals to V naught C omega sine omega t plus pi by 2. As you can see, this pi by 2 is the phase difference which is in positive. So the quantity V naught C omega is defined as a V naught by 1 by C omega. It is called maximum or peak value of a current. Or we can write up as I is equals to Im sine omega t plus pi by 2. This is the second equation. It is the expression for instantaneous current through a capacitor. So from equation first and second, we can find the value of a phase difference, which is a phase A of EMF of omega t, and the phase of the current is omega t plus pi by 2. Hence, the phase difference between the EMF and the current is a minus pi by 2 radian or a minus 90 degree. The phase difference between the EMF and the current is a phi is equals to omega t minus omega t plus pi by 2, that will become minus pi by 2. So for that case, if I'm just making the capacitive reactance, so capacitive reactance is defined as the opposition offered by a capacitor when current flows through it. It is given by Xc is equals to 1 by C omega, as you can see over there, C is equals to 2 pi F. The unit and dimension of capacitive reactance Xc are the same as that of a resistance. In terms of Xc, the RMS EMF is ERMS is equals to IRMS into Xc, where IRMS is the root mean square value of a current through a capacitor. If I'm just talking about the unit, so unit of XL or Xc or R is equals to R ohm, like ohm simply, and dimensional formula ml to T minus 3 A minus 2. Phasor and vector diagram is a pure resistor or a pure inductor and a pure capacitor. This is a summary of that. Now I am going to the question zone. That will be only 3 or 4 questions I am taking for the more elaboration and for enhancing your conceptual knowledge also. So in an AC circuit containing only capacitance, the current leads the voltage by 180 degree, lags the voltage by 90 degree, lead the voltage by 90 degree, and remains in the phase with the voltage. Here we are talking about, like I am talking about the capacitance. The correct answer for this question is option 3. Moving ahead. Next question. When an AC source is connected across a resistor, the current leads the voltage, the current lags behind the voltage, the current and voltage are in the same phase, the current and voltage are out of the phase. The correct answer is 3. The current and voltage are in the same phase. So this is all for today's class. I hope you like the session and get some more knowledge about this chapter. Thank you for watching this video, everyone.